Well, hello everyone. My name is Michael Buswell, and I am a remote student out of working out at Via Space out of Cocoa, Florida. And essentially, I wanted to go over with you guys today a really cool application of composites in the aerospace industry, and specifically about rocket nozzles. Now, the reason I wanted to go through this is because I've actually dealt with this firsthand a couple times and continue to do so, and we've actually found some really cool, interesting new composite manufacturing methods that I'd love to share with everyone. So kind of moving on, I figured it'd be a good idea to kind of go over the rocket nozzle background. So essentially just kind of going over what what the case is and why composites would potentially be a good reason for this application. And for those of you that weren't aerospace engineering students and didn't get to go through combustion class or any rocket classes, this is basically the gist of it. I'm obviously oversimplifying a lot, but the basic gist is we're trying to take advantage of accelerating combustion gases through a throat and actually expanding it through a nozzle. So then we're actually increasing the Mach number of the exhaust velocity so that we can actually generate thrust. Now the problem is that at the actual throat, where the area is actually the smallest, there's a really massive heat transfer going on, because essentially if you think about it this way, you're shoving all the heat that's being generated in the combustion chamber into a smaller area, so there's a greater heat density there that's trying to make its way and actually erode the nozzle, or actually erode the throat and the rest of the nozzle. So basically what I'm trying to get at is that this is probably one of the worst operating conditions on the planet, requiring some of the most advanced material engineering and or thermal engineering to actually satisfy this condition, because we're actually seeing temperatures from upwards of 2,000 degrees Celsius all the way up to 4,000 degrees. And then you're actually seeing pressures between 0 and 3,000 psi depending on what stage you're at in the combustion and where you're at in the atmosphere. Now, a lot of this actually depends on the engine design itself and what kind of combustion constituents you have in there, what kind of additives, what kind of oxidizers, obviously, and all the different things that kind of go into your specific case. But those are kind of some rough numbers, and you can actually see on the right-hand side, there's actually a CFD analysis of the actual heat map going on inside of the nozzle to kind of help you get a better idea of what's going on. And then on the right side, you can actually see a live fire picture from a hot fire we did last summer. Now, I'm trying to get at is that you can even see there is that even 18 inches away, you're seeing 1,500 degrees Celsius melting low carbon steel. So essentially, we have really strong material requirements for something that can resist these high temperatures, resist these high pressures. It needs to be strong and resist cracking. And it also needs to be corrosion resistant, lightweight, and as cheap and easy to make as possible. So this is where we have essentially three types of solutions to this: metal, ceramic, and composite nozzles, where metal are the kind of historic solution to this problem. And we're going to kind of go through that real quick just to kind of show you what's been done and why composites are probably the best bet for this. So in the past, metal rocket nozzles and combustion chambers have been the kind of go-to, and that's mainly just because there was not that much advanced material engineering going on at the start of rockets. And so essentially the best way that they found to actually keep the metal from melting, because if you noticed, low carbon steel, and those steels are melting around 1,500 degrees Celsius, and our temperatures are above that around 2,000. We got to keep the temperature down in order to actually keep the geometry of the nozzle and keep the thrust where we need it. So that's where in the past a lot of people have resorted to cooling through they call it regenerative cooling, and basically you're just taking advantage of radiative cooling by having your liquid oxygen or your other oxidizers or cold fluids running on the opposite side of the combustion surface, actually driving the temperature down and keeping the metal from actually melting. Now, in the past, there is regenerative cooling through cooling passages in the nozzle and combustion chamber, and there's also another popular method called film cooling, where they actually inject this fluid at a high velocity along the nozzle and throat to try and actually create a film barrier to try and keep the actual hot gases from being in contact with the metal wall itself. But as you can imagine, this is kind of dangerous because essentially you're injecting more highly combustible gases into an already combusting area, and if you get a chain reaction, you can get the whole thing to blow up. So it's a very concerning problem that kind of shows you why you want to try and have a material solution to this and not a radiative cooling solution as much as possible. Now, more modern metal rockets nozzles are getting more and more advanced through metal 3D printing and some fancy alloys, but the problem is that these machines can be very, very expensive, and obviously metal 3D printing is not completely there yet, so there's still a lot of kinks to work out. So this kind of moves us to the next type of nozzle, which are called ceramic or ceramic insert rocket nozzles. Now, these types of rocket nozzles are actually they're a little bit newer, but they're not necessarily unheard of in military programs or even older programs in the 80s or 90s. The thing is that these have become much more mainstream and are available for commercial use, and you can find these types of nozzles inside NAR class 1, 2, or 3 rocket motors that you can buy online. So basically, these are types of rocket nozzles that are very cheap and easy to make. Now, the problem is with these types of ceramic nozzles is that they're quite fragile and they're prone to cracking. Now, the problem is if you have a nozzle crack, you increase surface area and then you lose pressure, and you get a whole host of other problems, and then now you have a leak path that will then make its way to the outer casing, and then you're going to melt your outer casing, and then the whole thing falls apart. So there's a lot of issues with having these types of ceramic inserts due to cracking or even having interfaces between the ceramic plates. And mounting these types of ceramic nozzles is actually quite difficult as well. But they can be quite cheap, so that is really enticing for a lot of companies and manufacturers, and a lot of the times companies will resort to using graphite, silicon carbide, or titanium diboride for these types of nozzles, depending on what kind of your budget is. And then these can either be formed, basically pressure formed in a mold and made a block, and then CNC'd into the shape that you need, or you can pressure form it directly into the shape that you want your end use part. But essentially that's is quite a process, so you essentially have to make supporting hardware specific for that. Now, this kind of leaves us to the final case, which is our composite rocket nozzles, and I'm actually going to go through a few different ways that are actually used today, and a few different ways that are actually coming out and are like cutting edge. So for instance, full composite nozzles and combustion chambers have been a dream for quite a while, but due to not having the right manufacturing methods and even analysis methods and testing methods, we weren't really. It's been very difficult to characterize composites and actually test and verify a lot of these things going on. And in the past, carbons have been pretty expensive to make and form, and are just now getting a little bit cheaper and more understood. But the benefits of these types of nozzles are they're hard to deny, especially with the great strength to weight ratio, the great ablation properties, the better crack resistant, and then the safe method of not having to actually regeneratively cool these areas and keep combustible oxidizers and fluids away from the actual engine, increasing safety of the overall vehicle in total. So you can see why these are pretty enticing. But I'm going to go through 3 different methods of manufacturing, hopefully quickly enough to kind of give you a good idea, but not too quickly. But basically, we're going to go through these 3 different methods. They all essentially use the same type of reinforcement and the same type of matrix, depending on just different proprietary blends. So for instance, for the most part, the reinforcement we're going to be talking about in these composites are either glass or silica fibers woven into strands, fabrics, or blocks. And then the matrix are carbon or phenolic binders that are actually baked into the part itself. So we're going to go through method 1. It's a 4D weave, so this is probably the most technically complex method, and you can see kind of why over here on the right. But I was able to find a research article by Yang Liu here, and essentially this goes over the fabrication of these carbon-carbon nozzles in slight detail, and you can kind of see the pattern up here where they were able to form a block and then essentially CNC out the shape of the nozzle that they wanted. And essentially what it is they have sheets of this carbon fiber with these toe directions of W, X, and Y directions, and then you actually have a Z direction with carbon rods fit in vertically, so you actually build up a structure. Now, basically, for what they described in this research article is that it's T300 toe woven into a 3D fabric, and then the carbon rods are added in between the fabrics every 4 millimeters, kind of shown up here. And each rod is 1.5, and each toe is about 2 millimeters. Now, the matrix, it was described as a coal tar pitch. Now, I didn't find much more information on that or how what else they did, but essentially it was just described that heat and pressure was added, and then that essentially reconditions that coal tar pitch into carbon-carbon with the carbon strands itself. Now, the simplest way to make these is actually to go ahead and make a net block shape. So you can kind of see that in the middle graphic right here. And then you actually throw it into a CNC and you mill it down to shape. Now, this is not very easy to do, but it's easier than the other way. And essentially this way is extremely tough on CNC machines and drill bits, and a lot of time are completely destroyed in the process. Another more difficult way of doing this is actually making this block in shape, and then pressing it, and then actually adding the heat and pressure in the mold in its final shape. Now, I don't have much more information on how to do that. I wasn't able to find much, but that was one method. Now, a cheaper, more available method for most people and manufacturers out there, and what you're actually seeing here is a company called Scorpia Space Launch Company, and they're a company that's partnered with Microcosm. So Microcosm is a big space company that's been around for the 80s, 70s, 80s. They've done a lot of satellites, a lot of rockets, a lot of moon landers, things like that. So they know what they're doing, and essentially we've been working with them to actually go ahead and make some nozzles like this and other composites. But essentially what it is that you actually go ahead and use a process called filament winding, or type winding is a more common method with thicker toes. But this essentially uses simple carbon fiber from Hexcel. They're just rolls of different types of filament, and you pick what you need depending on your application. And then you go ahead, you make a mold, you determine your geometry, you make a mold, then you go ahead and you actually wrap your part on a CNC winder, and I'll show you a picture of it, but this is essentially one on the side for a tank, and you can actually see the fiber lay patterns after just a few lays, but essentially these toes are laid in a specific geometry to try and maximize strength for weight. And you can see that has an interesting pattern here where there's a big curvature, but on something more flat, you can kind of see that the rolls are more of a hoop wrap design where they kind of go around the part. Now, for the reinforcement, as I said before, it's mainly Hexcel. It's carbon fiber, single toe, and essentially you just use as many of these as you need, and you actually have a bath where the toe gets soaked in and then gets mixed with the phenolic binder. And I added HexFlow from Hexcel. It's their proprietary blend. Works really well with their carbon. And you can find some that are actually room temp cure, which is really, really nice. So you can just wind your part and then you just let it sit outside in the shop floor for 8 to 24 hours and let it cure. But some other types you're going to actually have to find an autoclave and throw it in there and add some heat and pressure. Now, I realized I went over filament winder or the process, but this is the actual machine. So it's basically got this filament carriage that goes back and forth with some fiber spools, and then it has a resin bath. So these are where you put all your fiber spools. They get all mixed together, get thrown into a bath, go through a little eyelet, get conditioned, and then get guided around your parts. And you can kind of see here, this is a multi-axis mandrel winding machine with your tanks above and below. So this is kind of what they use to actually go ahead and make nozzles like this, or tanks in different objects. So that's kind of the most, I would say, accessible way to go ahead and make composite nozzles and combustion chambers and pressure vessels and different things like that. The problem is that, again, you need to make sure to pick the right toe and the right resin binder, and essentially to go ahead and satisfy your conditions, which is very, very difficult. But there's actually another way that is more in tune with 3D printing and the newer types of additive manufacturing. And there's this company called Continuous Composites, which own a platform called the CF3D, which essentially uses a big, we'll just say a big metal robot arm with a little head on it that essentially has a resin bath, and it takes dry off-the-shelf fiber, just like that filament winder machine I showed you before. And those are really cheap, really accessible spools. And you essentially throw it in with this machine, and you pick your resin that you want, and they offer a few different blends, and they actually partner with a chemical company that actually makes their proprietary resin, and they will make specific blends for whatever case you need, which is very interesting and very nice. But essentially the cool thing about this is that they actually go ahead and use UV snap resin curing. So they print the part and then they instantly snap the part or the fiber in place by curing the resin instantly with UV light. So then essentially you're creating an end use part as it's being built. The cool part about this is that you can unlock all sorts of geometry that you really can't get even with normal 3D printing. And I've seen this machine bridge 6 feet gaps in between structures. So it can essentially print a bridge in place. which is very, very cool. Now I added a link up here so you can click if you get the PowerPoint. But essentially, this is the machine. This is the basic gist. You make your part, you program the G code, you throw it in the machine. It can print on a flat surface or existing surfaces, and it basically builds and snaps it in place. And it can use different types of tow. It can use carbon fiber tow or glass fiber tow. And then the snap cure resin, there's two different main types, and you can kind of see the difference here. The first type is for more generic applications, where you can use whatever tow you want, carbon fiber or fiberglass, and then you use the polymat matrix binder, and then essentially you get a glass transition temp of less than 220 degrees Celsius. So you don't want to be using this for high temperature parts, but this is great for just normal structural parts. And then you actually have another type where you snap cure the part in place, but then you actually have to throw it into an autoclave afterwards, and then it becomes a full carbon-carbon part, where this is the real application for aerospace, where you can actually go ahead and use it for nozzles and different things. And the cool part about this whole machine is that they're always getting volume fiber fractions of greater than 60% and the porosity of less than 2%. And you can actually see here some layups of this machine, and I actually have got some sample parts that you can see on the left here of it laying down, and you can actually see that this is how they cross fibers as you're going over the same area to make sure you're not getting a Z buildup in one area too much. But it's really cool because essentially the application for this is to make a nozzle like this, where you can lightweight the wall as much as possible, and then you can also go ahead and print specific directional supports with tow in the exact direction you need. So this is kind of where composites have gotten to with the aerospace industry, and it's kind of cool to see that they're mixing it with new additive manufacturing methods to make things a lot cheaper, faster, and more affordable for everybody. So definitely keep an eye out on Continuous Composites as a manufacturing, because they're expanding to airplane parts, rocket parts, and just general consumer parts as well. So I just figured that was a kind of a cool thing to share with everybody, and I look forward to seeing everybody else's presentations. Thank you.